Alright, today's topic is topological sort. I really like this topic because this topic is indeed seeing in action some graph traversal algorithms. So there is a real need, which we are going to cover in a moment, and by using DFS, BFS, some graph traversal algorithms, we can actually solve a real problem. So that's why it's a nice and interesting topic. Let's get started. First off, when we say topological sort, we are looking for a specific order of nodes in a given graph. But there is a specific conditions of this graph to be able to run topological sort on it. And I think it's going to be more clear if we first look at the applications. So, we use topological sort for prioritization. Let's say you have some tasks to do and there are some dependencies in between. Some tasks have to be finished before other tasks. In such situations, topological sort is very useful. Another application is curriculum building. You have some courses which are prerequisites of others, right? So without getting an introduction to programming, can you get advanced programming? Probably not. Wouldn't make sense. And in curriculum building, you have such dependencies, so it's a good application example for topological sort as well. And finally, job scheduling. So this is very close to tasks or prioritization. So you have some stuff and you're going to execute them, but some of them need to be executed before than the others. So this doesn't mean that for everything you need such dependencies. There can be some completely independent tasks, which can be represented as a node, which doesn't have any edges, right? So still, there can be some dependencies too that you have to respect. And in such situations, topological sort is very useful. So now let's go back to the top of the slide. It says, it is defined on directed acyclic graphs. So let's not get afraid of the term. If we take a closer look, we will understand why this is the case. The graph has to be directed, meaning our edges are one way. Because think about it, if there are two-way dependencies, how can we resolve the situation? If A is depending on B and B is depending on A, where am I going to start the execution from, Suha? Just do it?
Maybe both.
Maybe both, right? But the dependency wouldn't make sense. So that's why it is defined on directed graphs. And once you represent things, that's how you're going to model things. So let's take a look. Let's say here you have CS 101. And here you have CS 201. And let's say CS 101 is a prerequisite for CS 201. So if we represent it this way, if the edge is directed, it would make sense, right? If I put it this way, you wouldn't know if it's both ways, whether CS 201 is depending on 101 or vice versa. So that's why it is defined on directed graphs. And now let's take a look at the second property of this graph, which is the graph has to be acyclic. What does that mean? So we are trying to build a curriculum here, let's say. And 101 is depending on 201. And 201 is depending on, or let's say CS 202 is depending on 201, which makes sense. So if 202 is also depending on 101, can we build a curriculum here? Again, we have the same problem, right? Which one are we going to start from? So that's why, by nature, this graph should not contain any cycles, so that we can talk about topological sort. So up to this point, are we clear? And when we think about it, like let's say we are given courses, we are given dependencies between them, we can easily generate such a graph, right? The dependency graph for all the courses. And once we create this graph, in order to decide in what order students should take these courses, topological sort comes into play. Does it make sense? So is everybody clear with what problem we are trying to solve? So we are given things and there are some dependencies between them. They can be courses, they can be tasks, they can be some prioritized traffic that we need to manage. Anything. And when we look at the graph that we can build from such situation, there are two properties we see. One, the graph is directed because the dependencies are directed. CS 201 is depending on CS 101. It's not like they are both depending on each other. And second, the graph should not have a cycle. Because if there is a cycle, if there is cyclic dependency, then we cannot indeed execute them. So this doesn't mean that if the graph that you are given has cycles that you cannot use topological sort. Maybe the question is also including the cases, oh, if there is a case that you cannot manage things, you should return -1 or you should return 0. So the question might be asking it this way. But you guys should see why, if there is a cycle, logically we cannot get out of the situation, meaning we cannot come up with a topological sort for this graph, but that if we follow the execution with that order, we will respect all the dependency conditions that are given to us with the help of the edges. So, are we clear with the definition up to this point? Cool. Now, let's see, what do we mean by dependency? So, after we generate such graph, now let's take a look at here. How do we represent dependencies? If there is an edge between node A and node B, what does that mean? Does that mean node A is depending on node B? Or node B is depending on node A? Any answers? Node B is depending on node A, right? We can take a look at here. If we say A to this, B to this, there is an edge this way. We see that CS201 is depending on CS101. So likewise, like when you are learning such concepts, try to make it easier for yourself by coming up with a real world example. Because that way it makes more sense, right? If we just put ABC, it's going to be harder to reason about, or 0, 1, 2, 3, 5. But with course names, it's easier. So next time we can update these slides. Sorry, now it has numbers. All right, cool. So basically, when this graph is given, what we want to do is, for every edge from U to V, you should come before V. So for every edge we have in this graph, the source has to come in our output order before then the destination. So now let's consider some sorting of these nodes to check whether they are topological or not. So let's take a look at this. We start with CS101, and then we get CS201, and then we get CS202. And here we have CS101, and let's say here we have CS323, which is depending on CS101. And then we have CS323, and we have CS201, CS202. And then let's say we do CS323 here. And then here we have CS101, CS201, CS202, and CS323. So now we are going to check, we are going to evaluate each of these orders whether they are topological or not. So let's start from the top one. Who wants to go through this one? Any volunteers? Come on guys, it's easy. So like this is ordered, like now we are going to check whether this is topological or not. So who wants to do that? Nothing.
CS101 depends on CS201, which is correct. And
Or the other way around. CS201 is depending on CS101, right?
Oh yeah.
Yes.
But the last one CS323 doesn't depend on CS202, so the overall it's not.
It's not topological. Okay, then let's make it clear what the definition of a topological sort is. So basically, if our order has any violations of dependencies, then we say this is not topological. So in order to violate, for every edge from U to V, U has to appear earlier than V, right? And in order to violate this, V should be appearing before U. In that case, we say, hey, there is a violation here. So now let's see the edges. So 201 is depending on 101, right? We have this edge. And 202 is depending on 201. And we have 323 is depending on 101. So if we actually do it in the same way with the graph we put over here, So let's represent them like this. So now, once we take a look at it now, do you see any kind of violations? No, right? Like you can actually think, hey, if an edge source appears later than the destination, there is a violation. Because the prerequisite is not taken before the original course. So, now you say, this is topological. Good. Who wants to evaluate the second one? Yes.
No, it's topological because we're taking CS101 before the other courses, and we're taking CS201 before CS202. So the order of everything is different.
Yep. How about the third one?
It's the same as the first one.
Oh, okay, so let's make a change. It's not topological, right? Because we start with CS201 and after that we get CS101. But in order to be able to get CS201, we should have taken CS101 first. And that is not the case. So that's why this is not a topological sort. So are we clear with the definition right now? And what we are trying to achieve? Indeed, we are looking for one of these topological sorts. So the reason I wanted to give this example is to make it clear that there is no one correct way of getting all the courses. So there are multiple answers. Like you can execute the curriculum. There is no only one option. Not everything is depending each other. So, any questions up to this point? All right. In that case, let's move on. So we have a question here. Which nodes are safest to start execution from? So when it comes to course application, which courses are safest to take first when you look at the graph? Can you tell me something about their properties?
Courses doesn't depend on any other course.
Okay, and courses that doesn't depend on any other courses. And which ones are those?
In this case, it is CS101.
Yes, and how do you know that this course does not depend on any other course?
Any other node doesn't, not pointing to.
Yes. So basically, if a node is never a destination, right? Because like for each edge we can call this is our source. Since this is directed, this is our destination, right? Each edge is taking us from source to the destination, or from here to there. And if a node is never a destination, what does that mean? It means this course does not require, it does not depend on any other course. Therefore, it is safe to start execution from such nodes. So, how can we detect whether a node is never a destination node for any edge? Any suggestions?
If there is no edge that points to that node in our input, I think we should just check the that edges, right?
What do you mean? What?
If there is no any edge that points to CS101, for example,
Yes.
that should be the node we are looking for.
Yes. So how are you going to do that? So now let's try to make it in an efficient way. Because we need that information not just for CS101, right?
Yeah, maybe there might be another course.
Yes. So maybe let's say there is another course here. Let's say CS143. And it doesn't depend on anything.
So it's kind of a question. Should we find it on the first trial, or should we eliminate the nodes that are not possibly going to be our nodes first?
Well, like before building the solution, right now let's focus on the question we have in hand. So Nati suggested that we should look for nodes that are never destination nodes, right? So now we are trying to find a way to get all these nodes which are never destination. How can we do that?
We take an arbitrary node and traverse through it, and whichever nodes we didn't find could possibly be.
Interesting suggestion. But would this guarantee that, for example, if we start from CS201, we are gonna hit CS202, but we are not gonna visit CS323, right? Kind of a counter example. Nice try. What else can we do? What if we count something? What would you count?
I don't know, maybe count the levels it can go through, and then the one that has the maximum level is the source node. We count using DFS.
You count using DFS. You count what?
You count the levels it can go through from a node.
The levels it can go through, like the maximum, the deepest level it can go?
And the one with the maximum level is the source node.
I see your point. The one with the maximum level can be source, but it wouldn't guarantee that we are going to find all the source nodes again. So basically, that's what we are interested in right now, right? So we want to find an efficient way to reach to those start points quickly.
I think we can count the number of edges that points to us. After this process, we will have know which node has no edge that points to
Incoming edge.
Yeah, incoming
Yes.
edge.
So basically, the term that we can use here, thank you very much, Suha, that is the answer. We can basically count number of incoming edges for every node in the graph. So now let's take a look. How many incoming edges are there for CS101? How many incoming edges for this guy? This guy, it's 1, this guy, it's 1, and this guy, it's 0, right? And as a result, if we just go over this list of incoming edge counts and start from 0 ones, those are safe start points, right? Cool. Very good. Yes, so basically this is the answer that we get to. So how can we find the incoming edge counts? Like, this really depends what kind of representation we are using for the graph. But since in most of the cases we are using adjacency list, we can just take a quick look on the adjacency list implementation. Like at the beginning, we say in degree is 0. So in degree represents incoming edge count. And then we go over all the edges. And since this is a directed graph, each edge starts from the source and takes us to the destination. And we just increase the in degree for the destinations, because they are destinations, and we want to find out how many times a node is a destination. So if we do this, by the end, the nodes that have in degree equal to 0 will be great start points for us. So is everybody clear up to this point? Any questions? Yes.
Can we do this operation on this example maybe?
Can we do this operation on this example maybe? For sure, actually we did that.
Yeah, we did that, but can we have adjacency list on this maybe?
Yes, yes. So for example here, for CS101, you have CS323 and 201. And for CS201, you have only one edge that is outgoing, which is going to CS202. And that's pretty much it. We have 3 edges, and it's going to be like this. So you can, for the sake of completeness, we can make it like this. So our adjacency list is going to look like this. And when we are processing over this, since this is the destination, we are going to increase the count here. And then we are going to hit to 201, we are going to increase it here. And then we are going to hit to 202, we are going to increase it here. So in order to maybe make things more fun, what we can do is we can say CS10143 is also a dependency for CS323. In that case, let's add, oops, sorry, I forgot about this guy. 143, and it has an outgoing edge to CS323. And as a result, what is going to happen is, once we are processing, okay, we process this guy, and then 201 is 1. Okay, let's move everything. Let's execute our algorithm to make everything clear. So at the beginning, if you look at the first loop, we are just putting 0 to everybody, right? We didn't process anything. So at the beginning, we start with 0 incoming edge count in degree. And then we see 3, 2, 3. This guy is made 1 because it was destination. And then 2 or 1. So now this guy has become 1. And then 3, 2, 3. So now this guy has become 2. And then we have 2 or 2. This guy has become 1. Clear now? Cool. And teams, like, definitely feel free to ask such questions. If it arises on your mind, it means at least a few more people in the class are not very clear with that. And how much time did it take? Maybe a minute or 2. But it made things clear, right? So moving forward, it's going to make our job easy. So when you have such questions, please feel free to ask. It helps. Thank you, Sunan. And now let's go to the next step. So, okay, actually, maybe we can think a little more here. Alright, so we know that we are going to start from these guys with 0 in degree, right? When we take these courses, what is going to happen to our graph? Let's say we got CS143 first and CS101 next. What kind of change can this represent to our graph? Like, since we get these courses, is it okay to remove their edges from the graph? Because edges mean dependency, right? And if a course is taken, it means I can remove this from my graph, right? And when I remove this graph, what am I going to do with its edge? Is it okay to remove that edge from the graph as well? Now let's say we are trying to solve this problem by hand. No computers, you are given the courses, you are supposed to create the curriculum for the department. How would you do this? Looks like nobody wants to be Dr. Alefolius. Yes?
Actually, we can make a sign or if the course is taken, we can assign it to the show and the previous again.
So basically we can say this course is taken. Right? Any other updates shall we make to the rest? Like now that this course is taken, shall we also go ahead and mark that, hey, this has less dependencies now. Instead of 2 now, we have only 1 dependency left. That would make sense, right? So let's say after getting this course, I cut this edge and increase this in degree count by 1. Or like you can think of this as a logical delete too. It doesn't mean that you are going to go to adjacency list, remove the edge from there. You can mark that as edge used or anything. Or maybe just decreasing the in degree count might be enough for you. Who knows? We'll see. Okay. So there was another course which was a good start point, CS 101. Let's say we mark this guy too. And what if we also do the same thing? And also process its edges or mark them as deleted and then go and update the incoming degree count for the nodes that are coming next. This is going to be my graph now, right? So then, what can I do now?
Pick whichever one you want to go next to the ones with 0 dependencies.
We can actually apply the same logic, right? So the ones that have in degree count 0 right now, those are the ones which we can take because they are safe, they don't have any dependency, their all dependencies are taken care of. So we can do the same thing here and we can get CS102, CS201 let's say. And when I get CS201, what is going to happen? I'm going to mark this as done. And then since it has this outgoing edge, I'm going to delete this and I'm going to update this guy's incoming degree count. So I can actually apply the same logic, right? I still have some nodes which have 0 incoming edge. So this way, after CS201, I can either get CS323 and then finally finish with CS202, or vice versa, since they both have 0 degree. So are we clear with the solution? So when it comes to implementation, how is it going to look like? What things that we need to keep track of? We see that we know how to calculate these in degrees, right? After that, how can we find which ones have 0 in degree? Like when we are updating it, indeed we know that their turn comes, right? When something goes down to 0, we can detect it. Because every time we process a node, we go over its adjacency list, and for every node that we hit to, we decrease their in degree count by 1. It's basically logical deletion of the outgoing edges for the node that is just currently being processed. Right? And whenever a node hits to 0 in degree, what does that mean?
It can be processed.
We can immediately process it, right? So the same logic has to be applied though. Meaning, if that node has some outgoing edges, we also need to remove them, right? So, any algorithms that we have seen so far that can help us here? What are we doing here? Are we kind of traversing a graph? Yes. BFS. Nice. Tell us how.
So for example, now, say we're starting from CS101, and we have 2 nodes that we can process now, right?
Mm-hmm.
Oh, actually, no, I think we should start from 143.
Okay, so do you want to construct the graph again? Like, let's start from the beginning, right? Let me reconstruct the graph. Oops. I think this was our graph, right? And let's update the in degree counts to 0, 0, 2, 1, and 1. Yes.
Yeah, so now we start from node CS143, because it has an degree of 0. And now we can process the nodes, the children of CS143, which is CST323. And when we process it, that node is going to be 1.
All right, team. So now that we are clear with finding a topological sort with the help of BFS, now let's consider how else we can do this job. Okay, so let's take a look at this graph. Here we have this nice graph with 6 nodes. Nodes are numbered from 0, that's why the largest number we see is 5. Right, kiddos? Alright, so what if we go as deep as we can go? We start from somewhere and we go as deep as we can go. So in this graph, let's say we apply this algorithm. You start from anywhere, you go as deep as you can. Where would you end up?
5 to 1, 5 to 0.
Like, what's that?
Starting from 5, ending on 1.
5 can end at 1. 5 also can end at 0, right?
But the difference.
As deep as, so basically like as deep as you can go, meaning as far as you can go. So yes, one is deeper, but we don't care about the depth. Basically the idea is going as much as you can. And when you don't go anywhere, you're not able to go anywhere, you stop there. And this way, if we look at this graph, we see that we are going to end up at 0 and 1, right? No matter what node you start from, we are going to end up at 0 and 1. So now let's try to put it in the course context. By intuition, if we use this algorithm on the dependency graph of the courses, which years of courses do you think you are going to end up at? Let's say we have 5 years in our department.
You could go as deep as the 5th year course.
Yes, and which courses we are going to end up at?
The last one at the 5th year.
5th year courses, right? So is everybody clear with this part? Right, because like we go with the dependency edges. So earlier years courses have dependency sorry, like they are a prerequisite for later years courses, right? Logically speaking. And if we keep going as deep as we can in this graph, we are going to end up hitting to the last year courses. So the next question is, where do you think the last year courses should appear in the curriculum? At the beginning of the curriculum or at the end of the curriculum? At the end of the curriculum, right? So if we go as deep as we can, and then when we are not able to go anywhere else, if we get these guys into our result set, or let's say result list, what kind of list would it happen? Would it look like? So now let's try to apply this algorithm on this given graph here, and then see how it's going to look like. So we applied this algorithm, and what nodes we are going to end up in? 202 and 323, right? Let's say we added them to the result list here. Okay, now that we cannot go anywhere from these guys, we are going to return back, right? So after we return back from CS 202, and let's say this edge is gone because this guy is processed, right? It's in my list right now, here. And let's say this guy is also deleted. And if we apply the same algorithm right now, where we are going to end up? 201 and 143, right? And then I deleted these guys too. And I made my hand dirty. Finally, if we apply the same logic here, what's going to happen? 101 will be appended to the list, right? So how does it look now? Something looks odd, right?
It's reversed.
What if we reverse it? What if we start executing this list from here? Then what is going to happen? Is it going to be a result? A topological sort? How do we guarantee? When are we appending a node into our result set? When this guy is the node that is depending on other things, but nobody is depending on it, right? So basically, when nobody is depending a course, that course is appended to our result list. So when nobody is depending that course, what's that mean? That course is the deepest as we can go, right? So everything else has to be processed before this guy. Basically, this is the message we are getting, right? When we go as deep as we can go. Like once you hit to the last year's courses in the graph in your curriculum, this means all the previous courses have to be taken earlier, right? And since we keep applying the same logic again and again, as a result, we are building the curriculum in the reverse order. And if we execute our result list from the reverse order, indeed it's going to give us a very good curriculum, a topological sort. So for this approach, which graph traversal algorithm you think would be more proper? So which guy is just going deeper and deeper without thinking much about DFS, right? All right. So now let's see how our algorithm's logic would look like. We start the DFS from each unvisited node, because once a node is visited, it's already in our system. And if it has a not visited child yet, we go and traverse. Like here, basically, instead of visiting things, since I deleted them, that's why we ended up having something like this. But normally, we can just put a mark, right? Which is like a logical deletion. And if it has any unvisited childs, we go deeper. It's DFS. And if that is not the case, if we are done with all the unvisited children, it means it's our time to go into the result set. And by the end, we need to reverse the result vector as well. So are we clear with this algorithm too? Now, let's think about its time complexity. So, with this algorithm, how many times we are going to process a node? and by processing we can say we mark it as visited and then we go to its children. What's that? How many times? Like how many times can I add one node to the result set? Once, right? And when I come to this node, I go to its children. So think of DFS. Then it goes to its children, what's going to happen next? Is it ever possible to have a back edge? This is a directed acyclic graph. And if I can reach to my children with an outgoing edge, is there a way that that children can somehow come back to me? Of course not, right? If it was the case, then it means there is a cycle. So that's why it's guaranteed that there is no back edges, so I'm not going to hit to myself again. Meaning, every node is going to be processed once. How about edges? That's also once, right? And as a result, what's going to be our total time complexity? N plus n, right? It's a graph traversal algorithm. We use DFS. And we ended up n plus n. So things make sense. And let's say you are given a topological sort question. Which way would you prefer to implement? Would you go with BFS or DFS? DFS. Because usually if both do the job, then DFS is easier to implement, right? But this doesn't mean that you have to. You can also do it with BFS. I mean, we have also seen the code for the BFS, right? Like it was very simple. Like all about finding the in-degree edges at the beginning, and after that it's very simple. And in DFS, the beauty is you don't even have to worry about that. Like do we do anything about in-degrees, like incoming edges? Where does the DFS start from? Each unvisited node. So if we can have one for loop, which is checking whether a node is visited or not, and if it's not visited, going into it, this would do the job, right? Since there is no need for counting in-degree edges, I mean, it's not a difficult operation, but still, you don't have to deal with that. And the rest is pretty simple DFS implementation. You may prefer DFS implementation over BFS implementation. But it would be really nice to know both and to show off in the interview and say, hey, I could have done this with DFS as well. Or I could have done this with DFS as well if you did it with one way. So that's why I highly recommend feeling comfortable with both ways. And likewise, when it comes to graph traversal algorithms, again, like the ones that you can solve both with DFS and BFS, feel comfortable with both. Because there are some questions, DFS is going to be more handy than BFS, and there are some questions BFS is definitely more handy than DFS. Because if it's especially asking for shortest distance, minimum of something, then you know that BFS is the way to go. Because when you reach to something in BFS, it is guaranteed that you reach with the most efficient way. Whereas when you reach to something with DFS, there is no such guarantee. Maybe you went a very long way and there was one direct edge that wasn't processed earlier. So let's keep that in mind. But try to get comfortable with both, because graph traversal algorithms come a lot in the interviews, guys. So it's the number one topic, I think. Like if we just sort all the topics based on occurrence and treat DFS and BFS together for graph traversal, I think it's going to be the most popular question type. And if we all feel very comfortable with this, this is great news. It means as a team, we have 30-40% of getting accepted from the interview. Because many questions come, like I will say 30% wouldn't be an exaggeration. Like 1 out of 3 questions are usually graph traversal problems in the interviews. So if we get comfortable with them, it's going to pay us a lot in the long run. Alright team, so here we have 2 options. One option is we can go ahead and implement one question altogether here. So it's going to be like a learning how to approach session. Alternatively, what we can also do is, looks like we have enough assistants around. You guys can try to do this and we can go around and try to give you hints on how to implement it in DFS and BFS, like the given topological sort question. So which way would you prefer? Do you go, because like we had these lectures and we have been working on them for a while. So the additional logic of topological sort on top of DFS and BFS is very little. So for that reason, I am asking you guys, do you guys want it to be like a learning how to approach or directly like a practice session? Directly practice? Okay, and we are around. We will be monitoring whenever you guys have a question. You can ask us. Then let's do it this way. And again, normally if it was a purely new topic, definitely we would have it like a learning how to approach. But since it's the BFS plus little details, this way might be more effective at the moment. And let's finish with the quote of the day. And the quote of the day says, you attract what you are, not what you want. So if you want great, then be great. Thank you very much, everyone. And that's it for today.